I want to be the very best, like all the other stat students ever was, except was wouldn't be the right verb. Let's talk about continuous distributions, okay? And we're going to start by imagining a frequency histogram of actual data we've collected. We went to a Justin Bieber concert and we asked them how old they were, okay? So here is the count for how many said this age, that age, that age, okay? Now, if I wanted to ask probability questions for this, I would ask things like, what's the probability that the age of a randomly selected person is less than, let's do 15, okay? And these bars are 5 years each, so it's 5, 10, 15, 20. So the probability of less than 15, notice I'm not including the 15, so I would take 15 and take everything less. So that's the 5 here and the 10. I'm going to shade these guys in red. That's the probability I want. What would I do? I would just add up how many are in each of these. It looks like I've got 1 here and 3 there, so 4. But 4 can't be the right answer. 4 isn't a probability between 0 and 1. It's 4 out of the total here. How many are there total? 100. At least if I was really good at drawing histograms, it would look like 100. I tried to make it 100, but some of my lines are a little off. 4 out of 100. Now, let's change the question to say, what is the probability that our random age would be less than 20? So now I've got this extra bar filled in. I'm going to add these up. I've got 1 and 3, 4, 5, 6. So that would be 10 out of 100. So with a histogram, you can see exactly what it would look like. Now, we may not have a histogram. We might actually have some theoretical distribution. So I'm going to smooth this over. See how I'm just drawing a line on top of my histogram? This line is called a density curve. And the density curve is for continuous distributions. It shows you what an area distribution looks like. Let me erase the histogram. Okay, so instead of having a histogram, we could just use this curve. And instead of having data that we're relying on, 100 people's data points, we could use some equation that's used to draw this curve, okay? So the probability that we get a value for an age less than 15, well, I draw a mark right here at 15, and I want to find that area. And if I knew the equation that made this line, I could find that area. I would want to use calculus, and we're not using calculus in this class. So we're going to start off with something that is so easy that you can just draw pictures and see it. But then we'll get to the normal curve, and we'll talk about how to handle that. What if I wanted the probability of it being less than 20? I would shade in that. In fact, let's make this even more complicated. I want the probability that I select someone whose age is less than 35 or their age is greater than 70. Well, that looks super complicated, but I can draw the picture easily. Less than 35 would be right here, and I want to shade in all of that area under the curve. Or greater than 70 is also going to be that area. And now if I had calculus and I had an equation for this, I could calculate what those areas would be, and that would be my probability. So you can see why I encourage students to draw the picture. If you were a really, really good artist and you could really eyeball this, you could tell me that probability just by looking at the picture. If I was to eyeball this, I would say, let's see, more than 50%, maybe 55%, 60%, right? And I'm not really good at art, so this is a challenge for me. Let's talk about one thing. What if I change this to be the probability of less than or equal to 35 and the probability of greater than or equal to 70? This is a continuous curve. Whether I include this line and that line or not doesn't actually matter to the area. The area starts from either 35 or from 34.999999999. It doesn't matter. You're going to get the same probability. So including an equal sign or not makes no difference to continuous distributions. It did for discrete in the last chapter, but not now.